Yeah, so my name's Weston Thelen, last name Thelen. I am a research seismologist here at the Cascade Volcano Observatory.
And can you tell us a little bit about this room we're in and what's going on?
Sure, so this room is called our operations room. And so obviously behind me we have lots of screens here. This is where we do a lot of media interviews because we have nice visuals. We also do some meetings in here when we're talking about activity at the volcano, and we do helicopter flight following when we're doing work at Mount St. Helens. And so this is kind of a multi-purpose room. It used to be an area before we had the current technology that we have now, where there would be drums back here, and so it would be a real area for congregation because it was the only place where you could come at the observatory and kind of look at the real-time data as it was going around these helicorder drums. I'm sure most people remember what those look like. Technology's changed. Now we can see all the things that we can see here on this screen at any computer terminal, either here in the office or at my computer at home or wherever I'm working. So the operations room here has changed a little bit, but it is still an area that we congregate to talk about things happening at the volcano.
And can you tell us a little bit about the monitoring network that's set up around Mount St. Helens now and how that information gets back here to the control room?
Sure. So Mount St. Helens is one of our best monitored volcanoes. And so there's a combination of lots of different instruments up there. We have seismometers, we have GPS instruments, we have gas instruments, we have webcams. All that data comes in at different times, but comes in to the observatory here and does so through various means. And so in some cases, we're using just cell modems to get data back. Sometimes we're using radios. Sometimes we're using satellite technology like Starlink, whatever we can do to get that data back. But that data comes back here within a second or sometimes even less than, after it's been recorded at the volcano. And so all that data comes in here. There are computers in the server room that are bringing that data in, collating it, and then doing some analyses to either determine if there's an event worth telling a scientist about, or maybe it's producing a product so that scientists can more easily interpret what's going on. Sometimes it's being shipped off to our partners. For example, we have a partner at the Pacific Northwest Seismic Network at the University of Washington that does a lot of our earthquake processing. And so all of our seismic data gets streamed right up to the University of Washington, and they get it a few seconds after we get it, and they're able to do a lot of the earthquake analyses on the volcanoes around the Cascade. So at Mount St. Helens, we've got this network, this really diverse network of instruments that's coming in. And as I mentioned before, it's a very high grade network. And so we have a ranking that we use where we basically rank these volcanoes based on a combination of their eruptive history and their exposure to population. And so that's called NViews, the National Volcano Early Warning System, and it's a ranking. And so there's several volcanoes in the Cascades that are very high threat volcanoes. And what that means is that they have an active eruptive history and there's a population that's exposed to the hazards from that volcano. And so for very high threat volcanoes like Mount St. Helens, we like to have a network that meets that threat level. And so that's a level 4 network. That's one that has lots of stations distributed around the volcano in a way that we can see the processes that are going on under the volcano. So that might be gas escape, it might be magma movement, it might just be faults moving. We can see all of that with a level 4 network like we have at Mount St. Helens.
Awesome. Can you tell us a little bit about some of the things that really grab your interest or would be an indicator of something that you want to follow up on a little bit more once you see that data come back in?
Sure. So I'm a seismologist. I look at seismic data first. And so the types of things that we would see when we might expect unrest at a volcano, or when a volcano might be telling us that something is going on underneath the volcano or in the magma plumbing system, we might see a lot of earthquakes. And so Mount St. Helens has several earthquakes a day, has several tens of earthquakes that are really, really small up in the dome. We know that. We can see that that activity goes on day to day, but if we were to see an increase in the number of events based on our looking at the data, then that would be something that would get our interest. Earthquakes also have a signature, and so some have a signature that has lots of crossings. So if you think about a seismograph, there's kind of the middle of the plot, and when that earthquake comes in, it is going either above or below that center line. And if it does that a lot, that's a high frequency signal. That's something that we typically see with earthquakes, whether they're at volcanoes or not at volcanoes. And that tells us that a fault is slipping, and that two sides of that fault, that crack or that fracture in the rock, are moving next to each other. And so that's a really common signal at volcanoes. Now, it doesn't mean that it's something that we ignore. It's just something that it's part of the story that we're trying to piece together as we're looking at the data that's coming in. There's another signature of signal called a long period, or sometimes a low frequency earthquake. And so what if the high frequency earthquakes are doing this, the low frequency earthquakes are much longer. They don't cross that middle of the graph as often. So they're very distinctive, and we often see those ahead of periods of unrest. So in the processing, we look for these things. When we see them, we know, based on our experience here at Mount St. Helens, but also our experience with our partners in other places like the Alaska Volcano Observatory, Hawaiian Volcano Observatory. Our colleagues around the world see this, and so these long period signals or these low frequency signals are things that come up before an eruption. And so that would be something, if we saw them in tens or hundreds, that's something that would definitely pique our interest. And in fact, in the 2004 eruption, that's exactly what we saw. We saw an increase in high frequency earthquakes, those earthquakes that look just like any other earthquake happening anywhere else in the Pacific Northwest, but they're very small and they're happening right underneath the volcano from faults just slipping. And then that trended into more long period earthquakes. And in the case of 2004, that was a really smooth transition. It was something that was pretty straightforward to understand what was happening and to forecast. And in fact, the USGS did a really nice job of telling people ahead of time and giving people a heads up, and it was a nice trend to an eruption. Now, that was a really lucky scenario. It doesn't always happen that way. In 1980, it didn't happen that way. It did ramp up, but then we had lots of earthquakes for months before the big May 18th eruption. In Redoubt in 2009, earthquake activity ramped up. It looked like it was going to erupt, and then it calmed down, and it was quiet. And that went on for a number of weeks, and then all of a sudden it just started right back up. High frequency earthquakes, then low frequency earthquakes, and it was erupting. And so while we can use these signals to help us understand what's happening under the volcano, we still don't have a clear enough picture to be completely certain when things are going to happen. And it's tricky, right? You're under rock here. We aren't looking through the atmosphere like meteorologists are looking at clouds, seeing a storm come in. We're trying to see what's underground and using, a good network, but one that still leaves us with lots of questions about what's happening under that volcano because we can't physically see it, and the things that we're using to understand those, be it seismometers or GPS instruments or gas, are giving us clues, but they're not giving us the full picture of what's happening.
Do the instruments allow you to tell the difference between if a tremor is caused by gas escaping or if it's magma movement? Are you able to get that kind of detail?
There are some cases where in good networks like we have at Mount St. Helens that we might be able to tell the difference between those two, but it's a really subtle difference. And in the midst of an unrest sequence where you might be ramping up to an eruption at Mount St. Helens within 7 days or so, sometimes it's hard to do the analyses to figure that out and be really certain of it. At times you can kind of look at it, understand the signal, compare it to other volcanoes where that process has been interpreted, and say, okay, these signals are the same, they're similar. That's probably what we're having, but the really detailed analysis probably isn't going to happen until after the eruption has happened. So it's really important for us to understand sequences at other volcanoes, right? It's important for us to know what happened at Redoubt in 2009, or what's happened with these different volcanic sequences and the Aleutians, or bring in experts from elsewhere to look at this data and say, hey, have you seen anything like this? And that's what we do here within the USGS, is that when we have an eruption someplace, a lot of times we're bringing in experts from outside and we're saying, okay, this is what's happening. Have you seen something like this? Or what do you think? Or, we're not all knowing. We're bringing in people who have experience from other places and trying to get as much information as we can, and then feeding that into our assessment of the volcanic hazard.
And speaking of the scale of geologic time, our ability to track this activity within volcanoes is fairly new. Has it been around long enough that we're able to kind of start distinguishing patterns within individual volcanoes, or are they still very much individuals who are unpredictable?
The answer is always, it depends, right? In places where we have lots of cycles of volcanic activity, we do a really good job of understanding kind of the patterns that lead to eruptions. So places like that are Kilauea, where we have lots of cycles. Mauna Loa is another one. Places where we've seen multiple eruptions, that's helpful. So St. Helens is another one where we've seen a couple of cycles of eruptions. We've got a good network that's there. We've been tracking the background activity for a long time. We think we have a pretty good sense of what's happening there. It can certainly be, it can throw a curveball. It could be slightly different. It could be very different. We're not closed-minded to that, but at least in terms of the volcanoes within the Cascades, having a couple of sequences to look at ahead of an eruption is really useful. When we look at the background activity at different volcanoes, these volcanoes all have earthquakes. When I talk about background activity, a lot of people think that I just mean that there's nothing happening under there. And in fact, it's the case that a lot of these volcanoes have earthquakes in their background, and they have swarms in their background activity. And so you might get a time period over a couple of days where you get 100 earthquakes. And we see that at different volcanoes in the Cascades. When we track that background activity, what we see is that each of these volcanoes has a little different behavior. It has a little different personality to it. It's responding to the stresses underneath the volcano slightly differently. That helps us understand how it might react before a eruption. But there's still a lot of uncertainty for us there. And so, we would, if we were to see a volcano that we hadn't seen in the Cascades erupt before, at least with the instruments that we have, the things that we would look for analogies. And so we would look for other volcanoes around the world that are similar. We'd look at eruptive sequences there. We might look at other volcanoes, we might take Mount St. Helens as an analog and say, okay, well, we've seen this kind of activity here. Maybe it's the same. Whenever you get a new system kind of erupting, there's definitely more uncertainty with the forecast or the understanding of the volcanic hazard than a volcano where you've got a couple of different cycles.
Do all of the volcanoes in the Cascade network kind of behave similarly, or are you seeing some kind of like different characteristics for the different ones?
It's a great question, and they all have a little different personality. And so, for example, Mount Baker has very, very few shallow earthquakes. Actually has quite a few deep earthquakes that look like something is that magma is either coming into the system or is cooling under there. And so that's sort of one end member where we really don't have a lot of earthquakes shallowly at Mount Baker. Now, go to Mount Rainier, we have a few earthquakes a week. Go to Mount Hood, and all the earthquakes happen at Mount Hood in swarms. And so I'm being a little bit flippant about all, but most of the earthquakes that are happening at Mount Hood happen within these swarms of activity. And so that's a really different look than what's happening at Mount Rainier, where things are much more, Mount Rainier might have a few earthquakes in a week, but it doesn't happen in a swarm. They're just kind of going along and happening kind of randomly throughout. Go down south and get to a place like Crater Lake where there's very few earthquakes anywhere in the system at Crater Lake. And so there is a real diversity of activity across the range. And there's some indication that might be because of where it is with respect to the regional tectonics and the regional stresses. And so in Oregon, we have extension. In Washington, we have compression because of the combination of the subduction zone offshore and actually the San Andreas and the Walker Lane pushing northward. That's generating rotation, and that gives us kind of different stress regimes in Washington and Oregon. So that is probably one of the main factors that's driving the different behaviors of these volcanoes. Now, there's obviously going to be differences in the amount of magma that's feeding into those volcanoes. What we are seeing with increasing precision of the dating of deposits is that volcanoes work in cycles. And so a volcano will be very active for a number of hundreds of years, and then it'll be very quiet for a much longer time period, maybe thousands of years, and then it'll be very active. And so, it could be that over geologic time, we're just in a time period where a lot of these volcanoes don't really have much going on underneath there because they're in a quiet time period, whereas someplace like Mount St. Helens is in a very active time period.
And we recently saw a little bit of an increase in activity at Mount Adams.
Mm-hmm.
Some new monitoring stations were added, some temporary.
Mm-hmm.
Could you tell us a little bit about how that came about, how the increase in activity was first noticed, and what the goal is of putting the new stations up there?
Sure. So Mount Adams is one of those volcanoes that has been very quiet in its history. And so we typically see one earthquake up there every 2 to 3 years. it also, going back to this NViews ranking, or this combination of volcanic activity and population exposure, when you put those together, it's not, Mount Adams is not at the highest threat tier. It's actually at the second tier down, which is still a high threat volcano, but doesn't quite meet the level that, say, Mount St. Helens or Mount Hood or Mount Rainier do right nearby there. And so this is kind of what we expect in a volcano like this, is to have some earthquakes, but not very many. And so because of that, the network around there has been very sparse. And in fact, all the stations that were around there were operated by our partner, the Pacific Northwest Seismic Network. And so we know based on the seismic network that's up there, what our sensitivity is, and we just started seeing more earthquakes than we're used to up there. Now, 6 is not a lot of earthquakes to have in a month at any volcano. But when you go from something that hasn't had any to that, then it's something that we felt like we needed to get some more details on. And in the case of Mount Adams, a lot of this was sort of an opportunity for us. If we can record more earthquakes up there, if we can see what's going on under there in a little bit more detail, then that's an opportunity for us to understand more about where the magma might be moving, if it's magmatically related, if it's fault related, if it's gas related. This was an opportunity for us to understand more about the volcano itself. And so we took we looked at the 6 earthquakes, decided, okay, we're going to try to get some more information about what's happening up there. And so took some areas of opportunity. And so these were spots where they were going to be accessible, and that we knew that we were going to be able to get telemetry or communications out, right? Because we want this data to come back in real time. And so we put these stations out, and we've recorded a few earthquakes, not very many. It has improved our ability to record very small earthquakes, but there really hasn't been a ton that are up there. And so we probably, the peak of the activity, at least as in the current state, has probably passed. And because of the winter kind of setting in now, we're going to wind up, I think, bringing back a couple of those stations because they are not going to survive the winter. And so we'll grab those, bring it back, and then kind of keep our eyes open to any activity that would be up there. If activity were to increase again, then we would be in a spot where we could really easily put those stations back out. But we never thought that this was a scenario where we were marching toward an eruption. The number of earthquakes was still really, really small. It was just outside of the normal activity for this particular volcano. So because of that, we just wanted a little bit more information.
So you talked about the ranking for threat level for the different volcanoes. Can you talk about the difference between Mount St. Helens and the lowest threat level? And is there one in the Cascade range that fits that lower level you can tell us about as a comparison?
I would probably have to pass you off to someone else to tell you about the volcanoes that are at the very lowest, because I only have so much hours in the day. And so, we're really sort of concentrating on improving the monitoring and interpreting the data from those really very high threat volcanoes and some high threat volcanoes. There's a couple of volcanoes out there that are kind of surprisingly on even a lower tier that look like the rest of your Cascade volcanoes. Mount Jefferson is one example in Oregon, and on occasion we can see it from here in the Portland Basin. It looks like every other Cascade volcano, but based on what we know about its volcanic history and the lack of population around it, it isn't even in the high threat, it's in the next threat level below that. And so that's an example of needing to know about both the population exposure, but really critically knowing about the geologic history of the volcano can tell you, really kind of informs that threat ranking. And so it's not just, oh, there's a stratovolcano, it looks like the other one. There's more nuance and detail there.
So you wouldn't necessarily put the same effort into every volcano that you would into Mount St. Helens, I think, just to be on the safe side.
I think that we are an organization that gets a certain amount of resources every year, and we need to basically allocate those resources in the best way that we can. And this NViews ranking is one way of doing that, and really allows us to prioritize the things that we believe are important based on population and geologic history. And so we, if all of our very high threat volcanoes were properly monitored, then we could roll down to the high threat volcanoes and start on those. And then if all those got done, then we would go down. Now, all that being said, we have volcanoes here in Washington that typically come out near these stratovolcanoes. So sometimes it comes out the summit, sometimes it comes out kind of the side. In Oregon, it's much more common to have volcanoes come up in these what are called distributed fields. And so they're in areas that are maybe where there isn't a volcano right now. And in that case, we're really dependent on the regional network that's run by our partners. And the first case, the first thing that we will see is we'll see a very strong swarm of earthquakes as that magma starts to really push on the crust underneath. And in that case, then we will, we understand something about what's happening there based on the regional network. We would be able to respond very quickly to put additional stations there and track that coming to the surface. And so, another side effect of the Adams deployment is that this is an opportunity for us to kind of practice how we deploy instruments, and having not just drills, but real opportunities to go out there and put these instruments in and exercise those systems is really good. And so if there was a low threat volcano that decided to come to life, then we would be able to respond to it very quickly. And it's kind of fun to root for the underdog. So there's actually a volcano up in Alaska that has had a very low threat ranking, and it's really remote, and all of a sudden it started kicking off, and it was, on a personal level, I was really pulling for it to overcome the odds here as a low threat volcano. And it did. It was great. So, all right, so what we have here is this is called a helicorder, and this is basically the data from one station, in this case over 24 hours. And so you read this like a book. So you start at the top left and you read across, and each of these lines in this case is a half an hour. And so you read across, and then when you get to the end of that line, you go to the next one. So it's just like a book, each of these lines being a half an hour. Each of these little blips here is a potential earthquake. Now, this station is September Lobe. It is right on top of the 1980 to 86 dome. It is as close as you can get to these earthquake sources. And so it records a lot of little blips that are in the dome itself. Now, there are some bigger things that it's recorded today. This is an event that was just north of the volcano. This is an event that's a little closer to the volcano. So those are just regular tectonic earthquakes that are happening kind of nearby the volcano, whereas a lot of this smaller stuff is happening right within the volcano itself. And so here, now on the right, we're seeing kind of a real-time feed across the last 4 minutes of several stations that are basically close to the dome and then getting kind of further away. So these ones are the closest, they're on the dome. These ones are kind of on the flank of the volcano. And so if you sit here and watch for long enough, you'll see that there'll be events that show up only on Rembrandt, this top plot, and September lobe. And those earthquakes are really just happening right in the dome of the volcano. Now, we have a very good network at Mount St. Helens, but there's still earthquakes that are happening that are too small to locate. So we can see that there's an earthquake, but if we can't record it on, we would like to record it on 5 different stations in order to get a good location on it. And if we can't do that, then it basically just kind of remains in the data, but it will never end up on a website because it's not big enough to get to have the right number of observations to get the quality of location that you would want to put on a map. And so, these seismometers, they are incredibly sensitive. And so if there was somebody walking by a station right now, which this HSR is the station that is right next to the climbers route on the south side of Mount St. Helens, we see climbers go by. This is why we need a network of seismometers, is because we know if it's happening in the ground or if it's big enough that it's going to record on several different stations. And just like volcanoes have different behaviors, stations have different behaviors. And a lot of times I like to use an analogy of kind of a crime scene, right? So you have this crime scene, maybe the police show up to this crime scene and they've got several different witnesses, and each of those witnesses has their own reality of what happened. And maybe they saw it directly, maybe they're around a corner, maybe they heard something, maybe they're just crazy. We have stations for all of those personality types. We have crazy stations that just record weird stuff. We have stations that are more sensitive. We have stations that are less sensitive. And so putting all those together, and if they're surrounding that earthquake source, then we can get a good location, and even better than a location, we can start to do more advanced things, like understand if it's slip on a fault, or if it's magma moving through a system, or gas moving through a system. And so, that's really the need for this. And Mount St. Helens is a really nice example of what we can do with the seismic network that has been around for a long time. We understand more about Mount St. Helens than we do about any other volcano in the Cascades. And the reason is that we've had more instruments on it for longer. And so there's a real correlation there. Here you can see this earthquake here is the same earthquake that's being recorded at Mount St. Helens, but we're further away here at Adams. And so just kind of underscoring how sensitive these things are. We can record a decent-sized earthquake at one volcano can be recorded at a neighboring volcano. The other large signal here is this little blip right there. But overall, there's not really much happening at Adams currently. I can tell you just based on the look of this signal that it's very calm up there. It's very quiet. There's not a lot of wind. And that's sort of what we've seen for the most part since we've put stations up there. There's just been maybe a handful of earthquakes that have occurred since those new stations went out.
So even though this is an earthquake that could be picked up by the sensors on two different mountains miles apart, it's not necessarily one that would be big enough for humans to feel.
Absolutely not. Yeah. Humans, it depends. There's lots of things that it depends on. I think that when you've got an earthquake here where rock is a little bit more competent, it's possible in a quiet scenario where you're sleeping or maybe you're not sleeping, but you're just in bed and it's very quiet and there's nothing else going on, that you might be able to feel something below a magnitude 2 if it was really close. But almost every volcanic earthquake at Mount St. Helens, nobody feels. And that was even the case when they were getting up to magnitude 3 and 4, was that people don't feel earthquakes up there. And it's because that rock has got so many cracks and so many, it's just such bad rock up there that it soaks up that energy and it really doesn't transmit very well, like it would if you were standing on granite, for instance, to the surface. And so there's, and that's the case at lots of volcanoes, that the earthquakes that are being recorded here, almost all of them that are happening at the volcano are not being felt. You really got to be getting up to magnitude 3, and you need to be at pretty close range. A magnitude 4, if you're anywhere but a volcano, a magnitude 4 will feel like a truck hits your house if you're close to it. But at the volcano, that material that the volcano is made out of really soaks that energy up very quickly and scatters it across. So actually there's a little earthquake at St. Helens right now.
Can you tell?
What I see is that it's recording on the summit, or on the dome station. The next nearest station, it's recording a little bit on, but really not even getting out to the flank. And so that's going to be something that's probably below 0 magnitude. So this would be a good time to talk about negative magnitudes. So the energy that is released in earthquakes is dramatically different from a small earthquake to a large earthquake. And so if basically we could just tell you what that energy release is, and it would have like an exponent of 14 or 22 or 26 or whatever. And it doesn't make any sense to us. We really want something that's on a more linear scale. And so as the source gets larger, as the earthquake source gets larger, the energy release gets much, much larger. And it's not linear. It goes, it increases much faster. And so what we do is we use a logarithmic scale to transform that increase in energy to a linear scale. And so what that means is that a magnitude 1 is 10 times smaller than a magnitude 2 and 100 times smaller than a magnitude 3. But a property of logs is that if you have a negative log, then it's not like we're soaking up energy. It's just smaller. And so it's really an effect of the original. Basically, we can blame Richter. He came up with the original kind of magnitude scale, and that was based more or less on a kind of a magnitude 2-ish earthquake in Southern California. And so with the sensitivity of the instruments at that point in time, that made sense. And so, that sort of was how things got, that's how the original scale got going. But now we're able to, because we're closer, because we have more sensitive instruments, we're able to record those smaller earthquakes. And so now to represent that really small energy release, we have to use negative magnitudes to get those really small values. This is a L4 seismometer. So this is a short period seismometer, kind of an older style. We don't use this particular type of instrument anymore, but the instruments we do use are more sensitive, but they're kind of in the same package. And so they're about this size. You can hear in this one, we like this one because you can hear it, hear that mass in there bouncing around. The equipment we have now is much more sensitive, so we prefer not to shake it. And yeah, we can go look at a few of these.
Is that something that would sit on the surface? Is it buried underground?
We try to bury it as far underground as we can reach. The further underground we get, the better. Yeah, so we have a map of the seismic network here, and the station names are next to them in red triangles here are the stations, the seismic stations themselves. This is the rim of the volcano. This is where climbers come up to peer in. And so what you can see is that we have a network that is very focused on the summit of the volcano, and that reflects our understanding of what kind of the most likely scenario is, and that is something coming out of the middle of the volcano, or out of the dome of the volcano there. And so this network is really well positioned to record things that are happening within the center of the volcano. We've also improved our ability to monitor debris flows that come out of the crater to the north and off the cone to the west here. Now, I've mentioned before, this is a network that is consistent with the very high threat level that Mount St. Helens is, but we can't just put this network in and then just step back and ignore it. There's a lot of maintenance that goes into providing a network that is a state-of-the-art network like we need to have at Mount St. Helens. So there's constantly kind of refinements that occur up here. Sometimes those refinements are forced. For example, the crater glacier was moving, has been moving since the 2004-2008 eruption, and it had already run over, or we moved a station before it got run over, Yellow Rock, and we put another station in kind of further out, and we actually had to remove that station this year because the glacier was starting to get too close, and there was rocks and things that were falling and getting close enough to the station that it was becoming a hazard for people that would work on that station. So we removed that. We wanted a little bit better ability to track debris flows, so we added some stations to track some of those debris flows. But also we're wanting to keep up with new technology, and so we're adding new sensor types like infrasound, which is just a kind of a very fancy microphone, records sound waves below our level of hearing. And what we know about infrasound is that explosions create infrasound, debris flows create infrasound. Those are things that we're interested in monitoring here. They help us, especially when the volcano's obscured by weather, which we're in the Pacific Northwest, it happens a lot. It helps us interpret our seismic data, helps us interpret other data sets when we have lots of different types of instruments that are lending clues to what's happening. Sometimes we find better sites. And sometimes we have new questions about what is happening at the volcano, and we decide that, okay, if we have this set of stations, or this this new station or this new capability, then we would be able to answer this science question. So all that kind of drives how we would change this network through time. We've got a couple different builds here based on the conditions that occur where we're installing stations. So this is our current high mountain design. It has 3 solar panels. It needs this kind of height because we get high snow loads here. And so we need the hut in order to provide structural support for the solar panels, but also so that we can get a solar panel up higher to get above the snow load to charge the batteries that are inside. Because if snow even gets over a little bit of the solar panel, this whole solar panel becomes unusable while it's covered. It also allows us to put instruments up here and keep our antenna. This is our radio antenna on the left here, this square panel that's shooting typically 900 megahertz radio signals, in this case back to our receive site inside the office. We have a webcam up here, and then above that webcam is a weather station that's bringing in data to a computer that sits inside the hut around the corner. So
it lets you do your job, basically.
Yeah, I mean, these are the systems, you know, the most important part of a remote system is keeping it powered. And so we can put all the electronics and all the things that we want to within the hut, but they don't work unless they are continuously powered. And especially in an area like the Northwest where we have short winter days, a lot of times we have lots of clouds, we have lots of snow. It can be a really challenging place. In places where we get less snow, or we don't get any snow, we can change our design slightly. This is also a design here behind me that we can basically pack in the back of a car. And so it's the same setup. We still have solar panels that are powering batteries inside of a box, but now this is something that we can pull apart, that we can put in a truck, we can drive up to a site and then pull it back out. If we want to put in the high mountain site, that needs to happen with a helicopter. We need to haul that in and drop it in. This is much more portable, but it's really restricted to places where we can drive, and it's restricted to places that don't have a high snow load. So that's why we have kind of the two different designs here for our domestic stations.